Hello all of you. So, in the last lecture we started discussing the thermodynamic integration method for the free energy calculation, and the way we have defined it is we need to know a reference state for which the free energy is known to us, and I call that the state 1, and then the system under consideration is my state 2, and then I assume some path between the two states which is characterized by the variable lambda, such that u2 and u1 are basically the energies that we get for lambda equal to 1 and lambda equal to 0, and in general we can define u lambda as 1 minus lambda u1 plus lambda multiplied with u2, and then we have discussed that we can also have other forms of this u lambda, and we have to perform it for many lambda values between 0 to 1. So, now let us look at the partition function for this particular case, where I have introduced an artificial variable lambda. So, for any particular value of lambda, I can define the partition function as the following, where the Boltzmann factor will have the u value for that particular lambda, and using the partition function I can then evaluate the free energy, that is minus ln q by beta. When I say I can evaluate, that is conditional to the fact that we have to evaluate q, and we have discussed that q is very difficult to evaluate in molecular simulations, and therefore we work with derivatives of q or derivatives of the free energy, which is something that is easier to probe. So, in this case we can look at the derivative of free energy with respect to lambda. So, now this is for constant value of n, v and t, because we are imagining along an arbitrary path defined by the variable lambda, and along the path the n, v, t are constant. That means all the other variables, control variables that we have, they are constant, only the lambda is something that we are looking the free energy derivative with. So, this gives me something like this using the definition of f, and dou by dou lambda of ln q gives me 1 by q dou q by dou lambda. Now, I put in the expression of q from here in the denominator, and then if I take the derivative of q with respect to lambda, what we have is the Boltzmann factor multiplied with minus beta dou u by dou lambda. In this expression the beta cancels out, and essentially what we have is the canonical average of dou u by dou lambda, where the averaging is done for a fixed value of lambda. That is where we are computing the derivative, and clearly we can do it for different lambda windows or different lambda points that we have in the simulation. Now, I can find the free energy difference by simply integrating the dou f by dou lambda with respect to lambda in the interval 0 to 1, because lambda is going from 0 to 1, and that gives me the free energy difference from the reference state, that is lambda equal to 0, and this is precisely what we do in here. And now you can see why I was telling you that we have to do it for many lambda values intermediate between 0 to 1. The reason is we have to actually evaluate this particular integral. So, to get the better approximation of the integral, we have to do it for many intermediate points, where I perform a simulation, I compute the canonical average dou u by dou lambda, and then basically we do the same procedure for different values of lambda, and then once I look at the integral, actually approximation of the integral, that gives me the free energy difference, right. Although it is not possibly the most efficient method for computation of the free energy, it is actually the most simplest method that is typically used in most softwares, because there is a whole liberty in which how I can choose the reference state, all that we have to do is simply turn on one of the interactions slowly, and as I was talking about the Lennard-Jones system and Lennard-Jones plus Coulomb system and so on, we can pretty much do it sequentially over many interactions that are present in the system. At any given integration simulation, we can slowly turn on one of those interactions that I am working with, and then we have a reference state without that interaction and the final state with that interaction, and all the intermediate values where you have intermediate or partial values of the interaction that is present, and that can be done over all the possible interactions. It's very simple, straightforward way of getting the free energy. Once we have the free energy, we can also find the chemical potentials from there, but in principle there can be other ways of finding the chemical potentials as well, and one of the methods is the Vidoms method. And the way it starts from is, again, the starting point is my canonical partition function and the partition function of the ideal gas. This is something that we have already discussed, that we can write the Helmholtz free energy as an ideal gas contribution and the excess energy that is coming from apart from the ideal gas contribution. So now I can define my chemical potential as the derivatives of the Helmholtz free energy with respect to n, keeping the volume and temperature constant. And since F is minus kBT ln Q, this pretty much looks like this. And now in here, if you look at it, so kBT comes out, and then we have dou ln Q by dou n. Now in this case, I could have done something like 1 by Q dou Q by dou n, that is what we have done in the earlier examples. But what you also can notice here, that n is always changed in the increments of 1. We can either insert a molecule or we can remove a molecule. So n is a discrete variable. So instead of doing the differentiation using the way that we have done earlier, in this case what we do is we write the derivative in the difference form. That is, I can write the dou ln Q by dou n as the ln Q value for n plus 1 case, keeping the volume and temperature constant, minus the ln Q value for the n case, keeping the volume and temperature the same as earlier, and this has to be divided by the difference n plus 1 minus n, and that is clearly equal to 1. So therefore what we have is kBT ln Q for n plus 1 Vt divided by Q n Vt, and there was a minus sign in front of that, and this is what we have in here. So we have used the difference form for dou ln Q by dou n because n is a discrete variable. So then we can find the partition function of system containing n particles and the system containing n plus 1 particles. Everything remains the same, but wherever we have n in there, I will replace with n plus 1, and therefore you may recall that I have chosen to represent n in the function of u because n is a variable in this case, and that is the reason why I was representing dsn as the integration variable, because that will change to n plus 1. So now if I take the ratio of these two that is required in here, we get something like this, that is basically having a prefactor multiplied with the ratio of two integrals, one for the case of n plus 1 and one for the case of n. So now we can further simplify this. So the first part of this, as you may expect, that is coming from the prefactor, becomes the chemical potential of the ideal gas, and the second bit of it, that is the part containing the energies, become the excess chemical potential, just like what you had for the excess free energy. Now we have an excess chemical potential that is defined as the difference between the chemical potential and the chemical potential of an ideal gas under the same conditions. Now clearly chemical potential of an ideal gas is a function of its density, and therefore I am writing it as a function of the density, and clearly there are analytical expression available for the chemical potential of an ideal gas. So now we can focus only on the excess chemical potential, and for doing that I will define the free energy change delta U as the energy of the system containing n plus 1 molecules minus the energy of the system containing n molecules. And then I can basically rewrite this particular expression in a slightly different form, because we note that this guy is essentially U S n plus delta U, and once we do that, then the first term in the numerator inside the integral becomes same as the denominator, and then we have an extra term something like exponential of minus delta U. And when we do that, then essentially what we get is a canonical average of exponential of minus delta U by kBt, and this is evaluated at a particular value of n. And clearly there was one integration variable remaining, because denominator is for n particles and numerator is for n plus 1 particles. So until the nth particle we have the same scaling coordinates, but for numerator we have one extra variable, that is s n plus 1, and that will appear in here. So therefore we have a neat looking expression for the excess chemical potential. Now how do we implement that in practice? So the ultimate goal is to find the canonical average of exponential of minus delta U by kBt, and the way we do that is we basically perform trial random insertions and we do not accept them. That is, we do not change the number of molecules in the system, because if we change the number of molecules in the system, first of all we will not remain in the canonical ensemble, and secondly now I would be looking at the canonical average of system containing n plus 1 particles. In this case I am interested in the canonical average of exponential of minus delta U by kBt for an n particle system when a new particle is being added or removed. So clearly we want to do averaging over an n particle system. So therefore we do not actually insert the particle, we simply perform a trial insertion, compute the energy changes, but then we always reject all such Monte Carlo moves. And by doing that a small trick, what we can then evaluate is a quantity something like this. So we can compute the arithmetic mean of the exponential of minus delta U by kBt for, let us say, m trial insertions, and this is pretty much my average of exponential of minus delta U by kBt. Now that kBt ln is appearing because it was appearing in the expression of mu x, that is excess chemical potential. So we have pretty much evaluated the integrand, that is the canonical average of exponential of minus delta U by kBt. This method is called the Vidoms method, and this method is again very popular because one of the advantages of this method is, since we are not actually inserting the particles, we do not have to worry about acceptance rates because all the moves are pretty much being rejected, right. So we can always find the energy change of a move. If we are not really interested in putting a particle inside the system, computing the delta U is a very easy affair. We can always find the energy change, be it a small change or a large change. Unless we are really interested in increasing the number of molecules in the system, we can pretty much have a simple job that we have simply a calculation of delta U that can be easily conducted. In fact, this method can be extended again to mixtures using an idea similar to the semi-grand canonical ensemble that we discussed earlier, in which case I will perform a trial transformation of species alpha into species beta, and we never accept that. So, just like we are finding the excess chemical potential for one component in the earlier example, that is right here, if I am doing transformation of species alpha into beta, we would be computing the difference of the chemical potential between the alpha and beta species, and generally the ideal gas contribution will cancel out. And therefore, not only this method can be used for single component system, but also can be extended very easily for a multi-component system. So, the next method along these lines is the method called the overlapping distribution method, which is somewhat more efficient in comparison to the previous method that we have discussed. Again, the goal is to find the free energy differences, and in this case what we do is we assume two systems, system 0 and system 1, and we define the energy change between the two systems as basically the difference in energy between the two systems, that is U1 minus U0, and both these systems are having the same value of NVT, but they can have different interactions, for example, because ultimately we are interested in the free energy difference. That is the reason why we are defining two systems. So, you should keep in mind that we never focus on computing the actual free energy, but we are interested in always the free energy differences, right. So, now once we have this particular variable representing the energy difference between system 0 and system 1, we can define two variables. One, that is the probability density of delta U when we are doing the Boltzmann sampling of system 1. That is to say that we are doing my Monte Carlo simulation in system 1, and for every configuration that we get in my simulation, I can pretty much map the same configuration in system 0 and compute the energy there, and therefore we can get a delta U, and this we can do it over all the steps of my simulation. So, in this case we are doing Boltzmann sampling of system 1 and we are finding delta U's. Now, this will of course have some kind of probability density. So, we can for example create a histogram and use that to find the probability density of delta U. Now, I can do the reverse. I can perform the Monte Carlo simulation in system 0 again using the idea of Boltzmann sampling or by Metropolis algorithm, and in this case for every configuration that we have in system 0, I pretty much map the same configuration, that is I copy the coordinates from system 0 to system 1 and compute delta U for that, and then I will get the probability density of delta U when I am doing the Boltzmann sampling of system 0. And in fact, we can do both of these. So, I can find P1 delta U and I can find P0 delta U. That is pretty much representing two different kinds of probabilities, one defined over system 1 and one defined over system 0. But in both these cases, we are basically looking at the same quantity, that is delta U, only the averaging or the method to find probability density is different. In one case, we are averaging over system 1 configurations, in one case, we are averaging over system 0 configurations. So, now I can find the expression of P1 delta U for instance, which is basically having this particular partition function, that is integration over the coordinates. In this case, we are using scaled coordinates. Of course, we have the volume term and the prefactors, but they will cancel out because we are looking at the ratio. And then we have pretty much the same thing in the numerator, but we have added a delta function that pretty much tells me that delta U is equal to U1 minus U0. So, the delta function will be meaningful only when delta U is U1 minus U0 or U1 minus U0 is equal to delta U, because we are basically interested in finding the probability density of delta u. So, only for those values of u1 minus u0 for which the difference is equal to delta u, this delta function will have a meaning, otherwise it is going to be 0. And therefore, if I am doing it over basically all the possible configurations, we are essentially finding the probability density of delta u. So, now since the delta function inherently is valid only when delta u is equal to u1 minus u0, I can replace u1 in the integral here by u0 plus delta u. That is what I have done here, and then the delta function remains itself, a simple rearrangement of equation. But now I can take the exponential of minus beta delta u outside, because I was looking at p1 which is a function of delta u. So, delta u is known to me. So, I can pretty much factor out exponential of minus beta delta u outside. And now what we have is the numerator that we will get for p naught of delta u, because now the delta function is being weighted by exponential of minus beta u naught. Still in the denominator we have the partition function for the system 1. So, we can slightly rearrange the equation again, that is we multiply by the partition function of the 0 system and divide by the partition function of 0 system, and by doing this small rearrangement what we see is that the blue guy in the expression starts to represent the p naught delta u, because the denominator is the partition function of the system 0 and the numerator is the delta function, but now weighted by the Boltzmann weights for the system 0. So, clearly we will have exponential of minus beta delta u because it has factored out, and this first term in red comes from the arithmetic rearrangement, and that essentially is the ratio of the partition functions in system 0 and system 1. And therefore, what we have been able to relate is the probability density when I am sampling over system 1 with the probability density that when I am sampling over system 0. Both of these are related, and since I can find both P1 and P0 in a simulation, I can therefore find the quantity in between, that is Q0 by Q1 exponential minus beta delta u, right. So, this is precisely what we do in the overlapping distribution method. So, I can rearrange that and I can write in the ln form, and what we have in the middle is ln Q0 by Q1 minus beta delta u. Now, the free energy is minus ln Q by beta, or beta multiplied by the free energy difference is the first term here, and this is precisely what we write here, and then you have minus beta delta u, and clearly we are computing the probability densities as a function of delta u. So, delta u's are known to me, this is something we can choose. So, pretty much we have a method where if I know P1 and P0 distributions, we can find the free energy difference between the two systems. Now, we can slightly rearrange that so that it is somewhat neater. So, I can define two functions f0 and f1 defined over system 0 and system 1, where I have slightly modified in a way that the final expression is simply f1 is equal to f0 plus beta multiplied with the free energy difference between the two systems, and by doing that the problem would be to find f1 and f0 distributions, and my free energy difference would be simply given by the difference between the two distributions divided by the value of beta. Keep in mind it is beta delta f in the final expression. I can use this method to find the chemical potentials. To do that, what I can do is I will make my system 0 as containing n particles, but n minus 1 particles are interacting particles and 1 is an ideal gas particle. in system 1 we can have n interacting particles with the same interactions as system 0, and therefore, when I take the difference in the free energy between them, that should give me the excess chemical potential, because excess chemical potential is the total chemical potential minus the ideal gas contribution. So, in one case we have one ideal gas particle, in other case we have none, and therefore, we pretty much will be looking at the chemical potential of one interacting particle minus chemical potential of one ideal gas particle, because all the other n minus 1 particles are the same into the two systems. And therefore, if I take my system definitions as above, we can pretty much compute F1 and F0 for these two cases, again as a function of P1 and P0 as we had defined, and using that I can compute the free energy difference that will be in this case same as the excess chemical potential of the system. So, now one of the key problems in this method is when we find these two distributions F0 and F1 for the two systems, these two distributions should somehow overlap, because if they do not have an overlap reason, let us say for example one of them, let us say in this case is like having a different range from the other one, in that case there would be problems, because ultimately we are computing the offset between the two graphs, the two distributions. The difference between these two is giving me a measure of beta delta F. So, if they do not overlap or if they partially overlap, clearly we can define offset over a smaller region or no region at all, or if we have to define it, we have to extrapolate one of those distributions, that is again not really the correct way of doing it. So, this method will work ideally when you have a clear overlap between the two distributions. That will be the case when system 0 and system 1 are not really very different from each other, when they are closely located in terms of the model that we are using, then in that case we may have an overlapping distribution. But as soon as the two systems become different in terms of the behavior, more and more parameters are different, in that case clearly the distributions will no longer overlap. So, the applicability of this method is only for the first case when there is a good overlap, and as shown in this example here. So, in this case this is my F1, this is my F0, and F1 minus F0 is the dotted line that you see here, is the bold line that you see here, and the dotted line is the estimate that we get from the Vidoms method, just to compare the two methods. And what you find is that both Vidoms method and this method gives you pretty much the same answer, except that this may be slightly more efficient in certain applications. In this case, however, this is the result we get from the overlapping distribution method, and this is what we get from the Vidoms method. So, clearly there is a big difference. Assuming that the Vidoms method was the correct result, we can see that clearly our simulation is not giving me the correct answer, and that has to be because the distributions are not significantly overlapping. This pretty much forms the basis for another class of methods that basically tries to match the two distributions by defining intermediate states between the two systems 0 and 1, where you always have some partial overlap between two adjacent steps in your sequence of steps, and that is the basis of the method called the multiple histogram method, which we will discuss in the next class. So, with that I want to conclude here. Thank you.